one-to-one and inverse functions. Let's start off with the definition of one-to-one functions. A function f is one-to-one if each output of the function corresponds to exactly one input in the domain of the function. This means there is a one-to-one correspondence between the elements of the domain and the elements of the range. In other words, we could have a function like f of x equals x squared, where we have a set of inputs being mapped to a set of outputs. And so we put things in like -2, 0, 1, 2, and this goes to a 4. This goes to a 0. This goes to a 1, and this goes also to a 4. This is a function. Every x has exactly one y, but it's not a one-to-one function because we have a 4 that came from two different inputs. So it's not a one-to-one correspondence. When we have a horizontal line test, we can use for this. Now, the vertical line test was used to see if a relation, a graph, is a function, and the horizontal line test further tests if that function is one-to-one. If it is one-to-one, no horizontal line can intersect the graph of the function in more than one point. So let's look at this first example on one-to-one functions just to see if they are indeed one-to-one. This function f of x equals 3x to the 4th. We can put that into our calculator, 3x to the 4th. And let's just do a standard zoom. There we go. And we can see if we would draw a horizontal line through that graph, it would hit more than one time. So this function is not one-to-one. If we go to this second function, enter it, x cubed minus 1, and look at the graph there. This is a complete graph. We can see any horizontal line drawn through that graph will only ever touch once. So this is a one-to-one function. Now, inverse functions. The functions f and g are inverse functions if whenever the pair AB satisfies y equals f of x and the pair BA satisfies y equals g of x. In other words, an input of A giving an output of B is what f of x does. An input of B giving an output of A is what the g of x function does. So they do the inverse of each other's operations. Note that when this happens, f of g of x equals x, and g of f of x equals x. In other words, when you compose them of each other, they both will equal x for all x in the domain of g and f respectively. The domain of the function f is the range of its inverse g, and the domain of g is the range of f. In example 2, we have temperature conversion. So when we want to convert from x degrees Celsius to y degrees Fahrenheit, we can use this function. And to convert x degrees Fahrenheit to y degrees Celsius, we can use this function. Our task here is to show that f and g are inverse functions. To do that, we're going to show that f of g of x equals x and that g of f of x equals x. So let's start this process. We start on the inside function first, the g function. And now the f function says 9/5 times some input x plus 32. That input is the g function 5x minus 160 over 9. Now we simplify. Well, 9 and 9 are gone. 5 cancels that once, and this 32 times. So x minus 32 plus the 32 at the end there, and that simplifies to be x. So we have this halfway verified now. Let's go ahead and do g of f of x. So g of f of x is 9/5 x plus 32. And the g function says 5 times some input x minus 160 all over 9. So I'm going to put my new input, which is the f function 9/5 x plus 32, and simplify from there. 5 times 9/5 x is 9x. 32 times 5 is 160. Then I have the minus 160 there and the 9 on the bottom. That gives me 9x over 9, which is x. Therefore, f and g are inverses of each other. In example 3, we're talking about inverse functions. We want to determine first if f of x equals x cubed minus 1 has an inverse. Now, if a function is 1 to 1, then it has an inverse. So here, f of x does have an inverse. All right, we're going to verify that g of x is the inverse function of f of x. To do that, we compose them of each other. So f of g of x is equal to, well, we'll do the outside function first, f of, and then inside we have the cube root of x plus 1. The f function says we take some input, cube it, and subtract 1. What is that input? It is the g function of cube root of x plus 1. Simplifying this, I get x plus 1 minus 1, which is x. G of f of x is equal to g of f of x is your x cubed minus 1. The g function says cube root of some input plus 1. The input is the x cubed minus 1. This gives me the cube root of x cubed, which is x. Therefore, they are inverses. Finding the domain and range of the functions, I see the domain of the f function, and we can denote that as d sub f. The domain of the f function is all real numbers. There's nothing that could cause a problem here. You can cube any real number and subtract 1 from it and be okay. What is the domain of the g function? The g function here is cube root of x plus 1. If you're not quite sure what the domain is. You could graph it and try and observe from the graph, but I know that I can add 1 to any number and take the cube root of it and nothing bad will happen. Now if it was an even root, such as a square root, I could take a square root of a negative number and then be in imaginary numbers, but with cube roots that does not happen. Odd roots are okay. So our domain for G is again all real numbers. Now the range for F, we stated above, the range for F is the same as the domain for its inverse. So it's negative infinity to positive infinity. And the range for G is going to be the domain of its inverse, the domain of F. So all of these end up being negative infinity to infinity, all real numbers for domain and range for each function. Finding the inverse of a function. To find the inverse of the function f that's defined by the equation y equals f of x, first we rewrite the equation replacing f of x with y. In other words, just dispensing with the function notation and writing y instead of f of x. Next step is to interchange x and y in the equation, defining the function. So everywhere you see an x, you write a y. Everywhere you see a y, you write an x. In the next step, we solve for y to make our new equation. In step 4, we replace y with the notation for inverses, which is f inverse of x. So let's find the inverse function of f of x equals 2x minus 1 all over 3. The first step is to rewrite it without function notation. Then we switch our x's and y's. Make the y an x, make the x a y, and now I need to solve again for y. I'm going to multiply both sides by 3. That gives me 3x equals 2y minus 1. Then I'm going to add 1 to both sides. That gives me a 3x plus 1 equals 2y. And then I divide both sides by 2. So y is 3x plus 1 divided by 2. The last step is to rewrite in inverse function notation that f inverse of x equals 3x plus 1 divided by 2. Let's graph f of x and its inverse that we just found on the same axes. Let's go here. We can say alpha y equals n over d. This is 2x minus 1 over 3, and alpha y equals, using our handy fraction template, 3x plus 1 over 2. Okay, when we graph this, there you go. Maybe it might not look so impressive, but you can zoom and make it a square. And that way you can tell a little bit more about the graph. That way the x-axis tick marks and the y-axis tick marks are spaced the same, and you don't have that stretching of the graph horizontally because the x-axis is longer on your screen. The graphs of inverse functions says that graphs of functions and their inverses are symmetric with respect to the line y equals x. We can show that here on our graphing calculator. If you go to y equals and put in a third function of just y equals x, you'll see that line of symmetry, y equals x there. If we were to fold this graph, if it were on paper, fold it on that line of symmetry, the blue and the red graphs would lie on top of each other. In example 5, we have an investment problem. If $1,000 is invested for 3 years at interest rate X, compounded annually, the future value Y of the investment is given by this function, Y equals f of x, which equals 1,000 times 1 plus x cubed. To find the interest rate X that results in future value Y, find the inverse function of f of x equals 1,000 times 1 plus x cubed. In other words, the f of x function is going to use x as its input. That x is the interest rate X, and the output is going to be the future value. If we would find the f inverse function, that means that the x would be the future value. Your input would be the future value, and the output would be the interest rate. So we are trying to find a function that will give us the interest rate given a certain future value. So let's go ahead and find the inverse of this function. F of x equals 1,000 times 1 plus x quantity cubed. We first dispense with the function notation. We switch our x's and y's. X equals 1,000 times 1 plus y cubed. Now we need to solve for y again. Let's first isolate this part that has the y in it. So divide both sides by 1,000. Then we'll take the cube root of both sides to get the y out of those parentheses. Cube root of x over 1,000 equals 1 plus y. And one more step is to subtract 1 from both sides. So we have the cube root of x over 1,000 minus 1 equals y. Our last step is then to write that in function notation. So f inverse of x is equal to the cube root of x over 1,000, and the minus 1 is outside of that radical. Use this inverse function to find the interest rate that gives a future value of $1,331 in 3 years. So exactly, we're going to put the future value in for the x in that f of x function. That's the $1,331. And simplify from there. So we're taking f of $1,331. Okay, we'll just put this into the calculator now. So math, and option 4 is the cube root. 1,331 divided by 1,000, and then subtract 1. And that is exactly 0.1. We usually report interest rates as percent, so let's change this to a percent. that is going to be a 10% rate to get $1,331 in 3 years as a future value. Example 6 is concerning the velocity of blood. Because of friction from the walls of an artery, the velocity of blood is greatest at the center of the artery and decreases as the distance x from the center increases. The non-negative velocity in centimeters per second of a blood corpuscle in an artery can be modeled by the function v equals k times the quantity r squared minus x squared, with k greater than 0, x between 0 and r inclusive, where r is the radius of the artery and k is a constant that is determined by the pressure, the viscosity of the blood, and the length of the artery. In the case where k equals 2 and r equals 0.1 centimeters, the velocity can be written as a function of the distance x from the center as v of x equals 2 times the quantity of 0.01 minus x squared centimeters per second. Assuming the velocity is non-negative, does the inverse of this function exist on a domain limited by the context of this application? Most definitely. We have an x, x values can go in here, and definitely those are not going to be any negative numbers. X is the distance from the center of that blood vessel. So those are all going to be positive, and when we put those in, we'll always get a single output, so it is a function. And then further, they're assuming the velocity is non-negative, which is a good thing. So the velocity is non-negative. That means that we're only going to be considering the positives or 0 for this, and this is making this, by limiting that domain, a one-to-one function. If you look at this function as it is, it would not be a one-to-one function because it's a parabola, but we have limited it to only positive values of x, so it limits it to the right part of a parabola. That way it makes it one-to-one. So the inverse of the function does exist. And what is the inverse function? Well, let's find that. We'll start it up here. Y equals 2 times 0.01 minus x squared. And we'll switch our x's and y's. So x equals 2 times 0.01 minus y squared. Now our job is to solve for y. So let's go ahead and multiply by 2. 0.02 minus 2y squared. I can make this 2y squared equals 0.02 minus x. Divide both sides by 2. So y squared equals 0.02 minus x all over 2. And then y is going to be the positive square root of that. Only the positive because, make sure that this radical covers that denominator. Only positive because y is up here, it's the velocity, and x is the distance from the center. So both of those things can only be positive. We're going to say that y is only the positive square root of that. So the inverse function is v inverse of x equals the square root of 0.02 minus x all over 2. Now, what does the inverse function mean in the context of this application? I think it is worthwhile to go back and really dissect what the inputs and outputs mean for the v of x function. The inputs, they're using x. X is the distance from the center of the artery. And the output, they're using v of x, is the output. And the output is giving the velocity of blood. Okay, so the inverse function, what that means is that this output is now the input of the v of x function, and this input is now the output of the v inverse function. So it means that given the velocity of blood, we can determine how far away the blood is from the center of the blood vessel or the walls of that artery. All right, that does it for this section. Go ahead and try your homework and let me know if you have a question.